Good morning, everyone. This is the first segment of section 6.3. 6.3 is actually relatively short, but there's plenty of examples, so I'll try to work as many of them as I think is reasonable. But basically, this section is where we start incorporating some of those other identities, not just ones involving the Pythagorean, reciprocal, those kinds of sort of fundamental ones, but actually some that we derived in chapter 5, namely half angles, double angles, even possibly triple angles. There's a little bit of subtlety to them because what that does is it changes the periodicity part of the solution. But I will show you that here in just 1 second. Let me switch over here real quick. Okay, so first off, section 6.3, page 1. Okay, so let's take a look at this kind of a problem that doesn't, in all the problems that we've done so far, the argument has been just x, right, or theta or whatever. We haven't done anything weird with what's inside the arguments, and this is where we're going to start doing that. So rather than do it the way that the textbook outlines it, I'm actually going to do some things with multiple angles first, and then go back to half angles, because I think half angles are actually kind of, there's some subtlety to them, and you may miss it if it's the first time that we're seeing this kind of stuff. So let's do this. Let's say for all of these problems, and I've got maybe 6. I don't know that we'll do all of them, but here's the thing: is that we'll have to solve them in general, and then at the end, let's find all solutions. And I think these are all in radian, so this will be solutions where x is between 0 and 2 pi, which is pretty common, right? We've seen that before. So let's take a look at one that's really pretty simple here. How about 2 sine of 3x equal to 0? Okay, so we know how to manipulate this down to the point where we have, pretty quickly you're going to get that sine of 3x is equal to 0. Now, when we would solve these before, the next step was to say, all right, well, we pull out the principal root plus coterminal angles, and then we have the alternate root plus coterminal angles, and we kind of just started skipping that step to where we just would tack them on at the end. So here we have to be really careful, because we know how to solve this. If this was x, it would just simply be whatever that argument is, is equal to the inverse sine of 0 plus 2 pi times n. And that's exactly what ends up happening. So that we have 3x is equal to the inverse sine of 0 plus 2 pi times n. And there's the key, that we don't have it equal to x. And here's what people will do, is they will forget to divide this periodic term by the coefficient on the argument's variable. So this is, I'd say forget, this is the first time you've seen it, but this is kind of this critical step that as we're solving these problems in the previous section, we just kind of start tacking that on at the end and don't even note that it's there. So this does lead to extra solutions, because now when we divide by 3, all of these terms, everything on this side gets divided by 3. So this becomes x equal to 1/3 inverse sine of 0 plus, now instead of 2 pi times n, it's actually 2 pi over 3 times n. And now we evaluate this inverse sine term. It's going to be kind of boring. It's actually 0. So we have x equal to 2 pi over 3 times n. So any multiple of 2/3 pi. Now that's just the principal root. What about the alternate root? Well, the alternate root is going to be the same sort of thing. 3x is equal to pi minus the inverse sine of 0 plus 2 pi times n. And here, we can make this substitution. We know this is 0, but what you'll end up with is that x is equal to, excuse me, pi over 3 plus 2 pi over 3 times n. Those are all the solutions to this equation, all of them, and for some range of integers. Now we have to figure out which ones fall within 0 to 2 pi. Well, let's look at this one first. Obviously, 0 is one of the solutions because n could be 0. So I'm going to kind of save a little bit of space here. So x is in the set, is an element in the set that contains 0. And then going back to this one, now let n equal 1, we've got 2 pi over 3. And let it equal 2, we have 4 pi over 3. And if you let it equal 3, then you're at 2 pi, which is out of the range. It's equivalent to 0, right? So we've got 3 solutions from this equation. How about this one? Well, if we let n equals 0 here, we get pi over 3. And then if we let n equal 1, we get pi. And then finally, if we let n equal 2, we get 5 pi over 3, which is still in the range. So this equation actually ends up with 6 different solutions. And you're starting to think to yourself, well, hey, there seems to be this pattern where the number of solutions is related to the trig functions. And that is in fact true. One of the ways that you can kind of know when, in some sense, this is just a rule of thumb. It's not actually a hard, fast truth, but the number of possible roots or solutions to a trigonometric equation is the number of trig functions times the argument's coefficient times 2. Because for every trig function, you get 2 possible solutions, and then for the argument being a multiple of 3 or a multiple of whatever, then you get that many more. So notice from this simple equation with the trig function, there's only one sine of 3x. We ended up with 1, 2, 3, 4, 5, 6 solutions. And unless we have what's equivalent to multiplicity, in algebra, you talk about all the roots of a polynomial, and sometimes there's multiplicity of zeros. This is kind of a similar idea of what's going on here, is that sometimes you'll have one that turns out to be its own, its own supplement or something, which does happen. But anyways, so let's go to another problem, maybe just a little bit harder. So let's take -2 cosine, and I apologize, my email is blowing up in the background there. 2x, -2 cosine of 2x equal to square root of 3. Okay, so we want to isolate the function, so we end up with cosine of 2x equal to negative square root of 3, or square root of 3 over 2. And now we can write both the roots pretty quickly because it's cosine. But note, it's not going to be x equal. It's going to be 2x equal to plus or minus the inverse cosine of negative root 3 over 2 plus 2 pi times n. And so when we can evaluate first, or we can divide by 2, it doesn't really matter. The inverse cosine of root 3 over 2 is 5 pi over 6. So maybe I should go ahead and do that. I got 5 plus or minus 5 pi over 6 plus 2 pi times n. And when I divide both sides by 2 for this coefficient, I end up with plus or minus 5 pi over 12 plus pi times n. Excuse me, gosh. Okay, so the question then becomes, which these are all the solutions, which solutions fall within the prescribed range? Well, you would know then that there should probably be 4 of them. So the first one, if we just look at the positive branch, obviously 5 pi over 12 is in that range. And then if we add pi to that, so we let n equal 1, we'll get 17 pi over 12. Or, yeah, 17 pi over 12. Then we look at, if you add another pi to that, that's going to be outside of the range, right? So n can't equal 2 if this is positive. So taking the negative branch, we have 5 pi over 12, negative 5 pi over 12. Well, that's not in the range. If we add 12 twelfths of pi, we're going to have a 7 pi over 12, which is the next possible solution. I'm actually putting it down here, 7 pi over 12. And then if we add yet another, so that was where n equals 1 with the negative branch. If we add 2 pi, well, that's the same thing as adding 24 24ths of pi. Minus 5 will be 19. So we have 19 pi over 12. And there again, notice we had one trig function with the argument of coefficient of 2. 2 times 2 is 4 solutions. 4 possible solutions. Okay, so that's let's ramp it up a little bit. You start using some maybe a little bit more complicated ideas here. Okay, so I've made the argument before, especially in like chapter 5, where we were doing identities. I said, you really, in order to simplify these things, you've really got to get the same argument on everything. So as an example of what I'm talking about, let's look at this. Let's look at this this specific problem here. Cosine, and we'll use the same parameters. You know, find all values within 0 to 2 pi. So cosine of 2x minus cosine of x equal to 0. Now, it's very tempting to want to do something else, but you really need to get everything down to arguments that are just either x or 2x. And the reality is turning that into an argument with 2x is ugly, right? It's something we haven't even really done. You'd have to use a half angle formula, but in reverse. It'd be something under a square root. It's much easier just to substitute this with something that it's equivalent to, that is just cosine of x. And of course, that would be, I think we called it the second or third identity for cosine of 2x. So we can get this into a polynomial, but no, it's just a simple transformation of this into power series of that. So let's make the substitution. 2 cosine squared of x minus 1 minus cosine of x equal to 0. And then when I simplify, when I get everything in descending order, I have 2 cosine squared of x minus cosine of x minus 1 equal to 0. And this is a kind of problem that we've seen before, where you're just simply going to, try to factor it. If you can't factor it, then use a quadratic formula. But this one will actually, I think, factors pretty easily. So 2 cosine of x, one of them's got to be positive, one's got to be negative. I don't know which one's which. I hope everybody knows that this is the reason why. If this was positive, then they can either be both negative or both positive, but because that's negative, they have to switch signs. And I just need to figure out which one's which. So it looks like I need a -1 here and a +1 there. I think that'll give me, when I FOIL it out, my outside and inside terms equate to this, this cross term. So now I have 2 different trigonometric equations that I can set both of them equal to 0. So we've done this before, so I'm going to go a little bit quicker. You have from this one cosine of x equal to -1/2, which tells you that x is going to be equal to plus or minus. The inverse cosine of -1/2 is 2 pi over 3 plus 2 pi times n. Okay, and this one over here is going to lead to cosine of x equal to 0. This will give you the results plus or minus pi over 2 plus 2 pi times n. Okay, so when we try to figure out which solutions there are between 0 and 2 pi. This is all the solutions, by the way. And the book uses some squirrely looking notation to describe sets like this. You should practice it. I mean, we've kind of talked about how to write sets before, but it's not something I'm going to get too excited about. This isn't an algebra class. We're usually trying to find applied values. So x could be any one of the following. We've got 2 pi over 3, where if we take the positive branch and n equals 0, so 2 pi over 3. We could also look at the negative branch, but negative 2 pi over 3 is not enough. If we add 2 pi to it by setting n equal to 1, we're going to get 4 pi over 3. And anything else will be outside of the range. What about this over here? We've got pi over 2 is the obvious one. We add 2 pi to that. If we let n equal, say 1, it's going to be too big. Now, if we take the negative branch, negative pi over 2 is outside of the range. But when we add 2 pi to it, we end up with 3 pi over 2. Now, here's where this sort of intuition comes in. Look at the very beginning. We had cosine and cosine. They're the same functions, so we don't end up with that kind of multiplicity. But it was cosine, so 2 solutions, 2x times 2, 4 total solutions possible. And that's exactly what we got there. I think I might be running a little bit long here. And the next problem, well, you know, I think we run a little bit long, that's fine. I think I can squeeze in, well, no, I think I'll call it quits here. These have taken a while. We can start speeding them up on the rest, but I will see you in the next segment.